Good day, calculus students. Improper integral. It's finding the area, if possible, of a region that is unbounded. So a region that goes off in some direction forever. It's impossible to draw some sort of finite boundary around that region. We call that an unbounded region. This first example is trying to integrate 1 over the square root of x from 1 to infinity. When there's an infinity involved in your integration, then this is the indication of what's called a type 1 improper integral. Some functions may even go backwards to negative infinity up to 1 or some other number. I'm going to use Desmos to build an understanding of what's happening here. Keep in mind that this region keeps going this way. I couldn't show all of it, but we're trying to figure out how much green area there is. That's our goal, even if that region goes off forever. Show you a few things about Desmos. Let's first create the function that we want to integrate. So let's use f of x notation equals 1 over the square root of x. We want to do an integral from 1 to infinity. Now first I want to do some shading, and I'm going to set up my integral from 1 to b and create a slider. So I'm going to type in int for integral, 1 to b. The integrand will be f of x. I don't have to retype it. I can just refer to f of x and then put the dx next. Then add a slider for b. Say yes. For this slider, let's set b be as the minimum of 1, and then go up as high as, let's just say 10 for now. Step size 0.01. So I can drag b, and notice that depending on where b is, I get different answers here. Let's get some shading here to reveal what's happening. To get the shading, we want to shade above the x-axis but below the function. So we create a double inequality. We want do 0 less than or equal to y, less than or equal to, and then f of x. That shades below the function, but if you want to crop the shading, do some curly brackets right after the inequality, and then put the limits of integration essentially. We want to shade from 1 to b. So we'll say 1 less than or equal to x less than or equal to, and then let's put this b there. And now look what's happened here. I can drag b and create something I can interact with as I drag b around and get different answers for different amounts of area. And if I stop it at 10, then the current amount of area is this 4.324 figure. But the question is, what happens if b just keeps getting bigger and bigger and bigger? Because we're saying that we want b to approach infinity. We want this region, the shading, to go on essentially forever. Now your intuition might say, well, this isn't possible. If the region goes forever, then the area is going to have to be infinite in size. But let me quickly show you a demonstration of a visual where this isn't the case. Let's take a 1 by 1 block, and then imagine you cut it in half so that it stacks side by side. Now I'm going to cut this one in half and take the top half of it and stack it side by side. Well, that last one, I'm going to cut that in half and put it side by side. So far I have 4 pieces, and these 4 pieces all have the same area as the original block. It's a finite amount of area. But in theory, I could keep this up and create this sort of forever long sphere where these blocks get half as tall as they used to be and I go forever. Yet when I take all of these blocks and stack them up on top of each other again, you get a area of 1 still, even if there's infinitely many. Now, using this Desmos file, if I were to just go here next to b, and let's go to 100, and look what happened to the area. It became 18, and I went all the way out to 100, and then I stopped. Now let's just go out to 1,000, and look at the area. It became 61. Let's go out to 10,000. The area became 198. Go out to 100,000, the area became 630. It appears like the area is just growing and growing and growing. It doesn't seem to be stabilizing. So this is suggestive that the area under this region, if we go forever to the right, is going to be infinite. Now the formal work for doing this, I'm going to change this integral from 1 to b instead of 1 to infinity. Once I get an answer, I'm going to do a limit as b approaches infinity and see what happens to the expression. This 1 over radical x could be rewritten instead as x to the negative 1/2. Then I can just do the reverse power rule, add 1 to that power, it becomes 1/2, and then divide by that new power, which gives you a 2 coefficient. Plug b in first, and that 1/2 power just means radical, so it's 2 radical b, and then minus 2 radical 1. And then you analyze this expression as b goes to infinity. As b is approaching infinity, you're getting the square root of infinity, which is effectively infinity, right? If you put bigger and bigger and bigger numbers inside a square root, you're going to get bigger and bigger and bigger numbers without bound. And so what we would say is that this expression, this part especially right here, approaches, that's what this arrow means, infinity as b approaches infinity. This tells us that this amount of area under here is infinite in size. So we can put like an infinity sign for how much area is here. In such a case, we say that this integral, but with infinity, this integral is said to be divergent. That's the word we use for when the improper integral, and it's improper because this infinity implies an unbounded region. We say that it's divergent. Let's look at the next example. It's very similar, except I've changed the function to 1 over x. Let's go back to Desmos and experiment with the new function. There's our area from 1 to 10 under this function, and the answer is 2.3 approximately. Let's do 1 to 100. Notice it grew to 4.6. Let's do 1 to 1,000. It grew to 6.9. 1 to 10,000. It grew to 9.2. 100,000. 11.5. 13.8. 16.1. It seems to be growing. The area seems to be growing without bound as well. If I go further and further out, it doesn't seem to be stabilizing. This is an indication that the area is still infinite. Now the work we do here is very similar to what we did above. I'll do 1 to b, 1 over x dx. The antiderivative of 1 over x is natural log absolute x. Evaluate from 1 to b, so we get the natural log of b essentially. We're assuming b is more than 1, so b is positive. I don't need the absolute values on it. And minus natural log of 1, well that's 0, so we just get natural log of b. Well, now we just have to think what happens to this answer as b approaches infinity. Well, the natural log of infinity is infinity. Let's take a quick look at a graph of natural log. Now when you zoom out, the natural log of x is a growing function, and it looks like it's leveling off, doesn't it? Like there might be a horizontal asymptote. But let me blow that theory out of the water by graphing some sort of horizontal line. Let's say y equals 5, and then I'm going to change the x scale only. And notice that the function actually did pass y equals 5 at this location. So then you might say, oh, maybe the asymptote's higher. Maybe it's 10. Right? So let's change this asymptote to 10 and see if this graph will ever pass 10. So if I go far enough out to the right, notice what happens. It certainly does pass 10. Now we had to go out to 22,000 for the x-coordinate just to pass that y-coordinate of 10. So you might say, well, maybe 15. But if I go out far enough, you're going to see the same thing happen again. We're eventually going to pass 15 as well. Now we had to go out to 3,269,000 to pass the 15, but we eventually did. This logarithm graph is a very slow growing graph, but it grows forever without bound, meaning that no matter what horizontal line you make here, the natural log will pass it, will go higher than it. However, the natural log graph that you see here does have a vertical asymptote. It's at x equals 0 is the vertical asymptote, but there is no horizontal asymptote. This is helpful in making the claim that we make right here that this expression, natural log of b, does in fact go to infinity. So this suggests that we have an infinite answer here as well, infinite amount of area. Compare these two graphs side by side. They both start at 1 and both go to infinity. It looks like the graph above is thicker over here than this graph. In other words, it appears that the second graph is approaching the x-axis more quickly. This allows us to do what's called a comparison. And I'll write that comparison down here. And by the way, formally I should say the following as well. I should grab this, copy that, make that be an infinity again instead, and then say that this is divergent, or you can just say diverges. But there's this idea of comparison. I want you to note the following. 1 over square root of x compared to 1 over x. Which one is larger for all choices of x? Like if you were to think of x equals 4, right? I'm focused right here, but do it in both graphs. Which one had a higher y-coordinate when you look at the two? And it looks like the first one had a higher y-coordinate than the second one. This suggests that 1 over square root of x is more than 1 over x over the interval from 1 to infinity. You can also reason this way. X is larger than square root of x. And so if you have a larger denominator, if this denominator is larger than this one, then this fraction is smaller than this one. And also, we've shown on this second slide here that the amount of area under 1 over x dx is infinity, or it's divergent. We can conclude that the amount of area under the larger function has to be infinity too. Right? That should make intuitive sense. Just looking at these two images, if you were to overlap them one on top of the other, it should be obvious when you stack them that this region is completely contained within this region. And if the smaller one is infinity and it fits entirely within this one, then the larger one would have to be infinity too. This is called comparison, and it's an important idea that's going to resurface again in Unit 3 of this class when we do series. Okay, let's look at this new one, 1 over x squared. Let's do an integral from 1 to b of 1 over x squared. Now 1 over x squared is the same thing as x to the minus 2. I can do the reverse power rule on this. So we get negative x to the minus 1, that's just negative 1 over x. Evaluate it from 1 to b, and we get negative 1 over b plus 1. Now we get to ask ourselves, what happens to this expression as b goes to infinity? If that b that's in a denominator goes to infinity, then we get negative 1 over increasing denominators. Negative 1 over 1,000, negative 1 over 10,000, negative 1 over a trillion. These fractions are approaching 0. They're shrinking to nothing as b goes to infinity. So that means that all of this, therefore, is approaching 1. We can say that the integral from 1 to infinity of 1 over x squared dx is equal to 1, or you can say that converges to 1, or you can simply say, if you don't want to reveal the answer of 1, you can simply say that the integral is convergent. That means there is a finite answer. And the amount of area under this curve is all of a sudden 1. But what's sort of mind-boggling is that when you look at the two of these, it looks like they're not that different. Are you really telling me that one of these areas is infinity and the other is just 1? There's a huge difference between 1 and infinity, and the naked eye isn't revealing that difference. It feels counterintuitive. Let's see what the Desmos analysis gives us when I do something similar. Instead of 1 over x, let's do 1 over x squared. Let's go back down to just 10. Okay, so over here at 10, we're already so close to the x-axis, you really have to zoom in to see that the shading stopped at 10. But currently, the amount of area that's shaded right now from 1 to 10 is 0.9. When I go 1 to 100, it's 0.99. When I go 1 to 1,000, it's 0.999. 1 to 10,000, 0.9999. You see a pattern. It seems like the further I go out, the closer that the area is getting to 1. And if you go out forever, then we get to 1. So the area, the shaded area has an area of 1, assuming that this does head off there to the right forever. Okay, now I want us to look at the 3 examples and make a realization, because all of them were pretty similar. We did notice that one integral was an integral from 1 to infinity of 1 over the square root of x, that was x to the half, that was infinity. The integral from 1 to infinity of 1 over x dx, that also led to infinity. The 1 to infinity of 1 over x squared, that became finite. And so you might begin to wonder, well, what kind of power is needed on that x so that we have a finite answer or a convergent integral? It turns out that that cutoff is when the power on x that's in a denominator goes more than 1. So we can say the following. The integral from 1 to infinity of 1 over x to the p, let's put a power p there, dx, this converges if and only if. This IFF right here stands for if and only if. It's also a double implication, which is an important math symbol. It means that statement A implies statement B and statement B implies statement A. If and only if P is more than 1. When P was 1, we had this case, where we had divergent. When P was less than 1, such as this example, we had divergent still. But when P went more than 1, such as this case, we got convergent. All right, this idea of comparison that we introduced right here, that if you're able to do some sort of comparison, then you can make conclusions about convergence and also divergence. Let's go with what you're seeing here in this image. This function here, when graphed, makes this green curve, and that's in both images. I'm just repeating the image. The only problem with this function is that I don't know how to anti-differentiate it. So sometimes it's nice just to do a comparison so I can know whether or not this is going to be finite or infinite as an integral. And the comparison I'm going to do is the following. I'm going to take the original function and I'm going to ask myself, what would be an easier function to integrate is if it was just 1 over x squared. But the next question is, which of these two functions is bigger? Well, we can do that by, well, the numerators are the same, so let's compare the denominators. How does x squared compare to e to the x plus x squared? Which one's larger? Well, of the two circled things, the larger one is x squared plus something that's positive. So that means that as far as the fractions are concerned, the inequality goes this way, right? The fraction with the smaller denominator is the larger fraction. In fact, the blue thing that you see graphed here, I knew I was going to do this comparison ahead of time. That blue curve is the curve y equals 1 over x squared. And we want to see how much area is underneath that blue curve. Well, we've already done that, haven't we? Didn't we say that the integral from 1 to infinity of 1 over x squared, this is the one we just did above, we got an answer of 1. So the area under the blue is 1. In other words, it's finite. And the green curve is underneath it. It's contained within it. So what we can do, because of our comparison, we found a larger function whose area underneath it is finite, or converges. Thus, we can conclude that the amount of area underneath the smaller curve converges too. We can now state the comparison theorem in more detail. If the larger integral is finite, then so is the smaller integral. And then we're going to leverage the other one we talked about over here, and that was if you have an integral that represents a smaller amount of area than a different one, and the smaller one is infinity, then the larger one has to be infinity as well. If the smaller integral is infinite, then so is the larger integral. And this here, we'll call this the comparison theorem in words. And it makes a lot of intuitive sense. You have to be careful about these if-then statements. If I were to use implication arrows instead of words, they would look like this. An implication arrow that way and an implication arrow that way. These arrows are not reversible, meaning that if a smaller integral is finite, it doesn't tell me anything about the larger. Like, let's go back over here. Like here's a good example of that. If this smaller amount of area is finite, it doesn't necessarily tell me anything about the larger, right? Because the larger could still be finite, or maybe it could be infinite. And the other direction as well. Let's pretend that the amount of area under the blue, all this area under the blue was in fact infinity. If there's infinite area under a larger function, that doesn't mean anything about how much area would be under the smaller. The smaller could be infinity as well, or it could be a finite number. So the reverse of these statements are not true. Okay, let's move to type 2 improper integrals. Notice that there's no infinity here. So it looks like a regular integral at first glance, but when you graph this function, you get a function that has a vertical asymptote at 0. And over here is the graph of it. And as we head this way with the function, it goes up forever. This region, as described by this integral, is unbounded. It forms a forever long sphere going upwards. So 0 is the problem. What effectively we're going to be doing here is we're going to integrate from some number a to 1 instead and figure out how much area is here. And then we're going to drag this a towards 0. We'll do this with Desmos, and we will do it with symbols here. I'm going to change this integral to an integral from a to 1, and we're going to assume that a is some positive number but less than 1. So we're finding the area of just that piece right there. 1 over radical x is the same thing as x to the negative 1/2, so I'll just change it right now. The antiderivative of that, we've done this already, was 2 square root of x. Evaluated from a to 1. We plug in 1, we get 2 radical 1, that's just 2. And then minus, now plug in a, we get this result. Now we consider what happens as I drag this a closer and closer to 0. Square root of a is approaching 0 as a approaches 0. Meaning that this part here is approaching 0, meaning that overall this is approaching 2 as a approaches 0. And don't forget, to indicate that we're approaching 0 from the right, you put this little plus sign up by that 0. That means a is positive and shrinking to 0, as opposed to being negative and increasing to 0. All right, so then our final conclusion then is that this integral, that's 0 to 1 over square root of x dx, converges to 2. Or you can say simply it's equal to 2. You can just say that this is convergent. To say that it's convergent doesn't reveal what the area is, so it's nice to say both. It converges to 2. Put a area of 2 right in there. That's how much area is here, even though this region goes up forever. Now let's use Desmos to confirm this. But this time we're going to integrate from a up to 1. And let's do some shading between a and 1. Let's let a be as low as 0 and as high as 1. Step size 0.01. Okay, so a is it's a number between 0 and 1, and it's showing us the amount of area. Now as a gets closer and closer and closer and closer to 0, notice what's happening to the area. But let's go down to 0.01 and look at the area is 1.8. But now let's do 0.001, right? I'm just letting a get closer and closer to 0, and look what happened to the area. It's 1.93. Now it's 1.98. Now it's 1.99. Now it's 1.998, 1.999. The closer I get a to 0, the closer the area gets to 2. Okay, let's do 1 over x from 0 to 1. This is a similar issue. 0 is a vertical asymptote for 1 over x, so this is a type 2. And so we want to change that asymptote to an a to 1, or 1 over x dx. That antiderivative is natural log absolute x. Although I don't need the absolute value bars because we're assuming a and 1 are all positive. Plug in 1, we get 0 minus, and then plug in a, Again, I don't need the absolute values, but we get negative natural log of a. And the question is, what happens to this expression as a approaches 0? Now, the graph of natural log of x does not have a horizontal asymptote. So as you go to the right, as x goes to infinity, y goes to infinity as well. But as x approaches 0, imagine points on the green graph going left. And as the x coordinates get closer to 0, the points on the graph go down to y coordinates of negative infinity. Right, so this expression right here approaches negative infinity as a approaches 0 from above, which means that overall we're approaching negative infinity. We're just approaching positive infinity here. So this tells us that this integral diverges. The integral from 0 to 1 over x dx diverges. And if we go back to our analytical approach here, let's make this just 1 over x. Okay, so you can see that I'm just going from 0.1 to 1. That's how much area we're getting here, which is 2.3 something. But if I get closer and closer to 0, so let's go 0.01. Focus on the area answer, the answer for the integral. We're at 4.6, 0.001, 6.9. Keep going, 9.2, 11.5. I'm not getting stabilization. It looks like the area just keeps getting more and more. But what's happening here is that the amount of area this time is infinity, which is so mind-boggling when you look at the two regions. I mean, they don't look that different. Certainly this one is becoming a sharper spear sooner than this one is, but in one case, the case up here, the area is 2, and in the case down here, the area is infinity, even though both form a forever long spear going upwards. And then our last one, let's just see what happens when I have 1 over x squared. So this is going to be like integrating x to the minus 2 dx. Let's go, again do this a to 1, because 0 is where this function has a vertical asymptote. The antiderivative is negative 1 over x. From a to 1. Plug in 1 first, we get negative 1 minus, and plug in a, we get plus 1 over a. Now we're going to ask ourselves what happens as a approaches 0 from above. Right? When you have an a in a denominator, and that's approaching 0, right? Think of 1 over 1/10. Then think of 1 over 1/100th. Right? I'm just letting the denominator approach 0. And this first case is 10, the second case is 100. When I do 1 over 1/1000th, I'll get 1,000. When I do 1 over 1/10,000th, I'll get 10,000. You can clearly see that as a approaches 0, 1 over a is approaching infinity as a approaches 0 from above. So this is really approaching infinity minus 1, which is still just infinity. We get infinity out of this, and so we have, again, a divergent integral. Okay, and that's everything.